Okay, we're starting a unit that is considering all things that have to do with graphs, and what does the calculus that we've learned so far have to do with the shape and location of the features of a graph. And let's just start with a few old facts. If you have a positive derivative, we know that derivative means slope. So a positive slope means that you have an increasing function. Okay, so whenever your derivative is positive, your function's on the way up. When your derivative is negative, you have a decreasing function. And then when your derivative is 0, that means basically you have a flat function. And the majority of the time that makes what we call a relative minimum or relative maximum. It makes a peak or a valley. Usually a peak or valley. So the derivative would equal 0 at a place like this with a horizontal tangent line, or at a place like this with a horizontal tangent line. Or it could be where a function levels out for just a moment and then keeps on going in its direction, but most of the time it's a peak or a valley. So that's what we know so far. We're going to add some terminology and maybe a few new facts. These locations where the derivative is 0 or undefined, as it turns out, these are called critical numbers. A critical number is an x value where the function is defined. So we're not talking about holes or asymptotes. So we want the function to be defined, but it's a value where the function is defined, but the derivative is 0 or undefined. So critical numbers are going to happen at these peaks and valleys, these horizontal tangent lines, which are happening here, and I added one where it just leveled out, and here. And we're going to talk in this video about nice, neat polynomial functions that just kind of curve their way around with smooth curves. We can get into some functions later that deal with sharp turns and stuff like this. This is a critical point because the derivative was undefined. Sharp points mean that the derivative is undefined. Let's just add this at the bottom. Sharp points, and it doesn't have to be real sharp and pointy. It just has to be a point where it's not smooth. Even if it's a dull point, any point is considered what we would call a sharp point. This means the derivative is undefined. And another way to say that would be not differentiable. You're not able to find the derivative and evaluate it at that point. Just imagine the tangent line. You can't really put a tangent line on this sharp point because it would just teeter back and forth and it could go any which way. At a smooth point, there's only one tangent line. But sharp points, they can be critical numbers, but the derivative is undefined there. And the biggest addition to what we've done so far is going to be the second derivative. If the first derivative tells you where your function is increasing and decreasing, the second derivative tells you where your slope is increasing or decreasing. And if you think about an increasing slope creates what we call concave up. Any portion of the graph that looks like this, it's bowl opening upward. This has a positive second derivative because the slope is increasing. Now this doesn't have anything to do with whether the graph is increasing or decreasing itself, whether this graph's moving up or down. It has to do with what the slope is doing. So think about the slope here. It's a negative number, maybe it's close to -1. Then in this region, it's a negative, maybe half, it's a negative fractional number, less than 1. It gets to 0, then it gets to be a positive fraction, then it gets to be a bigger positive number. This increasing slope creates what we call concave up. And as you can probably guess, a negative second derivative creates what we call concave down. This is any portion of a graph that is bowl opening down. Okay, it's a decreasing slope. It has a slope that is positive, becoming 0, becoming negative. That's a decreasing slope, and we call that concave down. Points, let me restate this. I don't want to call this where the second derivative is 0 because that's not a proper definition of what I'm getting ready to define. I want to define an inflection point. This is kind of like a critical number, but one level more differentiated. It's the critical point of the second derivative, and that's not an official term, but that's how you can think of it. An inflection point is a point where concavity changes. So if I have a graph, and I'll just use this empty space over here. If I have a graph, remember we're dealing with nice, neat polynomials right now, that's just bending its way up and down across the axis. At some point, that graph, and I'm estimating it to be right here, has to change from concave down, bowl opening downward, to bowl opening upward. And 99% of the time, that's going to be where the second derivative equals 0. That's how we're going to find them. There might be exceptions, kind of like the sharp point on the last slide, but these are inflection points. They are where the second derivative is 0, and they're where the concavity changes. Okay, so here's an example, and for this one we're looking at the picture, which you normally won't be, but for this first time through I want to be looking at a picture so you can make sense of what we're doing. Relative extrema, that's min and max values. That's little peaks and valleys. They're called relative because it might not be the highest or lowest value that this function ever has, but on a small little window, it's a peak or a valley. So this point right here is a relative maximum because on, with a reasonable distance around that point, that's the king of all points. That's the highest. Now you can see over here, it ends up being taller, but on at least some kind of little neighborhood, sometimes it's called, that is the highest point. That's a relative maximum. So let's find those things. Alright, so first of all we want to start with the function, which is up here. I'm just going to rewrite it. It's 2x cubed minus 3x squared minus 12x. So this is all based on the derivative, finding these peaks and valleys. So y prime is 6x squared minus 6x minus 12. And I always want to set that equal to 0 because I'm looking for where this thing flattens out. That's a horizontal tangent line. That's a slope of 0. So to set something equal to 0, I want to factor it most of the time. So I'm going to factor out a 6 and be left with x squared minus x minus 2. And I'm going to factor that further to x minus 2, x minus 1. And that tells me that x is... x plus 1 was my factor. My x values are -1 and 2 because these are the values that make those factors equal to 0. So what I'm finding here is that this peak happens at -1 and this valley happens at 2. So how do we tell which one it is? Now remember, you're not going to be looking at a picture. I can tell obviously that -1 is a peak, a relative maximum, and 2 is a valley, but if you're not looking at a picture, we have to rely on other skills. If you think about what a cubic graph looks like, you should know that the left-hand value is the maximum and the right-hand value is the minimum, because cubic graphs in general look like this. So it should go maximum minimum as long as it's a positive cubic. But let's do the calculus anyway. because you're not always going to be able to just think about a function and what it looks like. So I know that I should have these critical values at -1 and 2. So I'm going to make a little number line, and we're going to do some test points. Something happens at -1, and something happens at 2. And I can plug in anything in that interval. And this interval would start at -infinity, and this interval would end at +infinity because no other changes are happening except at these two values. So I'm going to choose -2, 0, and 3 because they're just nice, easy numbers to work with. And what I want to do is plug these into the derivative, because the derivative will tell me if it's positive, my function's increasing. If it's negative, my function's decreasing. I'm going to plug into the factored version. If I plug -2 into this version of the derivative, I get -2, or I get 6 times -2 minus 2, which is -4, times -2 plus 1, which is -1, which ends up being 24, positive 24. And I don't really care that the number's 24, I care that it's positive. That tells me that my function is increasing from -infinity to -2. And I can see that happening again on this picture. It's increasing all the way up to this maximum point. At 0, if I plug that in, I get 6 times -2 times 1, which is -12, which tells me my function is decreasing from -1 to 2. That's happening here. And then at 3, I get 6 times 1 times 4, positive 24, increasing. So what we found, if your function changes from increasing to decreasing, if you go from walking up a hill to down a hill, you're going across the peak. So we have a relative max at -1. And if you changed from decreasing to increasing, we have a relative min at x equals 2. And you'll probably need to give coordinates, not just x values. So how are we going to figure out the exact point? Well, just plug in to the original y function, -1, and you're going to get 7. So that tells me that this maximum happens at -1, 7. I'm going to save you the time of watching me do that. And plus we're looking at a picture, so we kind of know the answers. If I plug 2 into my original function, I get 2 -20, which tells me there's a dip or a valley or a relative minimum happening at -20. All right? So that's how we find relative extrema. Sometimes they're called local extrema. How about inflection points? Where does concavity change? Let's do that. Let me get rid of some of this space so I can keep my graph. I'm going to go back. You wouldn't lose all this. You just have all this on another section of your paper. But we're going to do the same process except with the second derivative, because changes in the second derivative indicate concavity. So I'm going to back up to where I had my first derivative. I'm going to take my second derivative, y double prime. The derivative of 6x squared is 12x. The derivative of -6x is -6. And the derivative of -12 is 0. Just like I did with the first derivative, I'm going to set it equal to 0 to look for the changes. I can also factor out a 6 and be left with 2x minus 1. If I set that equal to 0, if 2x minus 1 equals 0, then 2x equals 1, and x equals 1/2. So at 1/2, that's the only possibility I have for a change in concavity. So again, with the test points, I'm going to plug in 0 and 1, and I want to plug these into the second derivative. If I plug 0 into the factored version of the second derivative, or I'm going to actually plug it into the normal version just to show that I could plug it in either place. 12 times 0 minus 6 is -6. So that's negative. That tells me I am concave down from -infinity to 1/2. If I plug in 1, I'm going to get 12 times 1 minus 6, which is 6, which tells me I'm concave up, starting at 1/2 and going for the rest of the function. So let's look at that. From negative infinity to 1/2, and if I wanted to plug in 1/2, I could get the actual value. It's right in here. And I'm not sure the actual coordinates, but it looks like it's between -6 and -7. I am concave down, starting at negative infinity up through that entire section of the graph, and then I become concave up afterwards. All right, so that's what a second derivative tells me, is my graph's slope increasing or decreasing, and what that translates into is concavity. So this is how we find inflection points and relative extrema of a graph. Okay, for our last example, I'm going to encourage you to pause this and try to find the extrema inflection points of this equation. I'm going to pause and write it all out and then come back with the answer. Okay, so here I am back with the work. This was a 4th degree function. We were looking for relative min and max and inflection points. So I started here with the first derivative. I set it equal to 0 and factored it, and those factors are equal to 0 at 0 and 3/2. And so those are our critical numbers. I need to make a little number line with test values, and it turns out that the first derivative is less than 0 or negative at -1. All right, I kind of just didn't even show the value just to prove the point that if I sub -1 into the first derivative, either here or here, I don't care what the number is. I just care that it's negative. It's less than 0, which means my function decreases. And I don't know if you noticed, but hopefully you did. This is an example of one where we have to double check, because after 0, my test point was 1, I also got a negative value, which means it kept decreasing. So that's not a relative min or max. I just noted that it's flat here because the derivative was 0, so I know the function's flat, but it decreased, went flat, and then decreased again. My other point of 3/2, after it I plugged in 2. The derivative evaluated at 2 was positive, so that means my function increases. So it decreases all the way to 3/2, and then it increases after that. Okay, again, those points, I find the specific points by plugging my critical points into the original function. So this one didn't turn out nice and even, but when I plug 3/2 into the original, I get -3.375. We'll look at that on a graph in just a minute. All right, so now to the inflection points. My second derivative was here. I factored it and got 0 and 1 as my possible inflection points. I want to check for concavity, so I plugged in my intervals were from negative infinity to 0, 0 to 1, 1 to infinity. My test points were -1, 1/2, and 2, and that turned out to be second derivative positive, negative, positive. A big mistake is not knowing where to plug in your test points. Over here, the test points need to go into the first derivative. Over here, they need to go into the second derivative, because that's the level that's telling you about increasing, decreasing, or concavity. So I have a concave up to down change, so I have an inflection point at 0, 0. The second 0 comes from plugging the first 0 into the original. That's what causes the confusion. Here I'm plugging into the second derivative to find this y value I'm plugging into the original. When I plug in my second possibility, the result's -2, so there's my other inflection point. So we'll wrap it up with a picture of this. So here's what we found. We found 0, 0 was an important point. It was a critical value because the derivative was 0, but you can see it leveled out, got to that horizontal tangent line, but then kept decreasing. What did change, however, was an inflection point. We went from bowl up, concave up, to concave down at that point. Then here at 1, the concavity changed back to bowl-shaped up, and that's what it did for the rest of its existence, all the way to the right forever. And then the other The relative min that we found was down here. All right, so I just wanted to get a picture of it while you're learning. Again, we're still dealing with nice, neat polynomials. We'll get into some more adventurous functions soon. But this was our first cram course on extrema and inflection points.